Given, n cities, flights as, from, to, price, SRC, DST, and integer k, return, cheapest price from SRC to DST under stop limit, else -1. One valid route is 0 to 1 to 3. It uses one stop, which matches k equals 1, and total cost is 700. A cheaper path 0 to 1 to 2 to 3 costs 400, but it has 2 stops, so it violates the limit. So the cheapest valid price is 700. Cheapest is not always valid under k. Here 0 to 1 to 3 costs 700 and fits k equals 1. 0 to 1 to 2 to 3 is cheaper but uses 2 stops, so it is out. Many people try Dijkstra first. On cities alone it always improves the cheapest cost label, which is fine when there is no hop limit. Here you also cap stops, so the lowest price path can still be illegal, like the 400 route that uses too many hops. Plain Dijkstra does not enforce that unless you change the state, for example city plus stops used. That is why we count hops with layered relax instead. Pause the big picture. Only cities 0, 1 and 3. Then watch flights versus relax passes. First arrow is flight 1. Second arrow is flight 2. 2 flights total from source to destination. K equals 1 means 1 stop allowed in the middle. That is exactly 2 flights on a valid route. At our 0 we only keep the start, source cost 0 and 0 flights counted so far. At our 1 we relax every edge once using that snapshot, so any update uses at most 1 more flight. At our 2 we relax again on top of our 1, so best costs may use up to 2 flights, which matches k equals 1. Our 0, our 1, our 2 are 3 edge sweeps, not city names. Together they match the 2 flight cap plus the start layer. Keep that picture in mind. Next we put the same layering on the full 4 city graph. Same beats on the full graph, each round grows reachability by 1 more flight. Each round only read previous and write cur, or you sneak in an extra hop in 1 round. Stop where the next round would count paths past the flight cap. Big picture, k plus 1 Bellmen Ford style passes. Each pass relaxes every edge once using only the previous pass costs. We run k plus 1 passes. Each pass walks every flight once and only reads the previous distance snapshot. Initialize previous, 0 at source, infinity elsewhere. We only read this row while we scan flights. Cur starts as a copy of prev. Each relax writes into cur while we still read frozen previous. Relax 0 to 1 for 100. Source cost is 0, so city 1 becomes 100. Relax 1 to 2 for 100. Previous cost at 1 is still infinity, so this edge does nothing. Relax 2 to 0 for 100. Previous cost at 2 is infinity, skip. Relax 1 to 3 for 600. Previous cost at 1 is infinity, skip. Relax 2 to 3 for 200. Previous cost at 2 is infinity, skip. Pass 1 complete, cur is the TMP row after every flight in this pass. Pass 2 resets TMP to a fresh copy of the new previous, then we walk the same flight list again. Relax 0 to 1 for 100. Best to 1 stays 100. Relax 1 to 2 for 100. Previous at 1 is 100, so city 2 becomes 200. Relax 2 to 0 for 100. Previous at 2 is infinity, skip. Relax 1 to 3 for 600. Previous at 1 is 100, so city 3 becomes 700. Relax 2 to 3 for 200. Previous at 2 is infinity, skip. Pass 2 complete, Ker now has the final distances for this K. Return the DST entry, 700, the cheapest valid cost under the stop limit. Time order is K plus 1 passes times the number of flights, because each pass relaxes every edge once while reading only the previous snapshot. Space is linear in N for the two distance arrays. Function takes N, flights, source, destination, and K. Comment, run K plus 1 passes, each pass touches every flight once. Build previous array of length N filled with infinity. Source distance is 0. Outer loop, pass runs from 0 through K inclusive. Start each pass by copying previous into Ker. Inner loop walks every directed flight edge. If the tail U is still unreachable in previous, skip. Otherwise relax, maybe lower the cost to V. After all edges, commit Ker as the new previous. If destination stayed unreachable, return -1. Otherwise return the cheapest cost at DST.